All right, thank you for that super educational presentation. I learned a ton. That was really fantastic, and I want to learn more from you later. All right, I just want to do a super quick announcement about some of the cool things that are happening just next door in the hackerspace. So, number one, create your own block of decentralized art at Node 3 anytime. So I think that sounds pretty cool. This is, we're sitting here listening, learning from amazing people, but if you want to get your hands dirty and create art, check that out. Number two, ERC 777 token standard Q&A at Node 5 at 4 p.m. So that's in an hour and 15 minutes. ERC 777 is really cool. Go learn about that. And number three, Vega protocol demo, which is happening at 3:45. Also in the hackerspace, that's in 1 hour. OK, up next we have Mihai Ciucu. I hope I pronounced your name reasonably correctly. And he is the co-founder and CEO of Blink, and he has a really awesome demo. So take it away, Mihai.
Hello, and great to be here. And allow me to tell you a little bit about what we're trying to do. With Blink, we're trying to develop a new distributed ledger. I think we wanted the slides for now. This is for later. I've got the slides here. Yeah. But no. OK, sorry. What we're trying to do is essentially a new distributed ledger technology that is as scalable as possible while offering sub-second latency. And the first question is, why are you trying to do a new distributed ledger technology? Aren't there enough models out there? And the way I want to start explaining this is using an analogy with databases. If you've probably done any web development, you've used SQL backend, MySQL, Postgres, Oracle even, or SQL. And if you've ever been more experimental, you've wanted to use a Mongo and NoSQL. If you've needed huge scalability, you've used Cassandra, Apache Spark. And the difference between all of these is that they have each a different usage model, and each of them organizes their data in a different way to facilitate that specific usage. Because you can get a lot better performance when you're more specific to your use case. And like, for instance, if Redis, which is just a key value store, has a hash database behind it. But if you're doing a more complicated Postgres, you'll use B trees, which just are optimized because you want fast disk access. And in the distributed ledger technologies, we just wanted to do the most scalable solution for the payments case, which was actually the very first case of a DLT Bitcoin. It wanted to do a proof of concept of how exactly you can do it. And it proved that it works, but with severe scalability and latency problems. So what is the payment problem essentially? You need a very high throughput system. Like Visa, everyone knows it can do 50,000 transactions in the worst of times in the Christmas rush. But Alipay can do hundreds of thousands in their greatest shopping day. And you also require extremely low latency. A finality can only be reached in like 15 seconds. But you don't want your customer, if they want to pay for a YouTube video or a song on demand, you don't want them to wait for 15 seconds before they can receive their product. They want to listen to it right now. And that's why you just want a very high certainty, not a guarantee, that that payment will usually occur. And there are also some other interesting facts of the payment problem that actually allow you to do some cool stuff. Like, for instance, no user has a huge throughput. If you're an average user, you just do a couple tens of payments a day, maybe 100, but that's rare. And if you're a merchant, then it's OK for you to use a more complicated solution and essentially just use multiple accounts. Now, how do you do scaling? Well, essentially, the natural way to do scaling is anything you can do in parallel, do in parallel. Like if I'm paying for a coffee in Berlin, it doesn't matter if someone buying a newspaper in London has their transactions recorded after or before me. If they apply these two transactions on the same global state in whatever order, you should get the exact same global state. The only thing that matters is the order of transactions that are applied to the same account. So that's why the underlying data structure that we use is essentially a mini chain for each account, where when you add a new transaction, you validate two previous versions of the sender account and the receiver account. And this allows you pretty much infinite scalability level. The only problem with this that you need is that if you remove a transaction, it only invalidates what happens afterwards. So that's why in our model, every transaction has to also specify a past consensus. We split all of our transactions into timed blocks or rounds, we call them. And every new transaction has to, instead of just signing the two accounts, also sign a past global state. It doesn't have to be the very recent one. It can be somewhere in the last 2 minutes. It just needs to mix everything back together. And this is reasonably okay to get scalability. But how do you get latency, though? Because even in this model, you still have to get consensus. Like, a transaction has to be in consensus or not. That's the way it is in a blockchain. It's either in a block or not. But what we do is we have a mechanism to get a very high confirmation that a transaction will be authorized before actually being in the finality. So the way we do this is we have a proof of stake guardianship mechanism where each account in the system is assigned a running node in the network proportional to their stake, which essentially acts as a gatekeeper for that account. The nodes get a large percentage of the fees that happen on those accounts, and they vouch with their funds that they're protecting these transactions against double spends. So essentially, if two random nodes, essentially, they are random because each node is seeded from a past state or from the same randomness source. All of the locker pairings are done from the same randomness source. And you know they're pretty much random. Even if someone somehow controls it, they can't, it is secure. But if they somehow manage, theoretically, to control it, they could just control a subset of nodes just for one locker, because everything else is independent. And pretty much, you get a lot of cool features by having essentially this dynamic sharding, because we switch lockers in each of the blocks, so they arbitrarily change. And for instance, even if when your locker is down in this 10-second round, you can just wait for another round and you'll get a new one and retry. And you also get another cool feature is that each locker can act as a spam protector on their own piece of shard. So if you want to have 100K TPS on the entire network, then you can assign a quota of transactions that each locker can introduce in the system. And now after that was essentially the architecture of the project. But when we started implementing it, we realized that there were a couple myths in the DLT space that I think everyone keeps repeating, and they are true partially. So for instance, the bottleneck is that all transactions have to run on all machines is the bottleneck for blockchain. Well, yes, you do have that bottleneck, but that bottleneck is much, much higher than people expect. So for instance, if you run a node, a server, that doesn't have to do proof of work that costs as much as a Bitcoin mining machine, you can get 2 very powerful Xeon processors that with 56 cores, and you essentially get a processing power that can handle 50,000 transactions per second on just one single machine. So the limitations are, yes, bandwidth, and the bandwidth of a machine, because it does have to receive all the transactions from the network, and the processing power. But machines are much, much more powerful than you believe. Like, the only thing is you have to optimize like it's 1999. And another different myth that we've seen and heard lots of times is that you have to make a trade-off between latency and throughput. What is your trade-off? And if you are doing a blockchain, there is a trade-off between latency and throughput, because you need to receive the current block in order to generate the next one. And the bigger your block, the longer your block time. But the way we parallelize transactions, this limitation is just not applicable, because we don't validate not the very, very previous state. We validate something in the last minute or two, which pretty much gives you kind of the same security guarantees on finality and immutability, but without having to essentially wait on everyone syncing to start any new transactions. And actually, I'd like to add another myth, that it's impossible to do any timing-based blocks or rounds. And I think that one is to do with some security vulnerabilities that have been discovered in NTP, the protocol that everyone uses. And you can patch it up reasonably easy. I mean, once you manage, you can do through the protocol itself a very, very simple synchronization of time. And after that, time is a universal constant. You can actually measure it. You can just have to have a clock, and that's it. So you can do secure clock synchronization. It is hard to do. And now, what use cases have we seen for something like this, where we want to optimize for low latency, high throughput, but just transactions? So micropayments is the obvious one. Essentially, there hasn't been a successful micropayments cryptocurrency out there. Like, since Bitcoin intended to be used for payments, purely for payments, and it ended up being an asset, essentially. But, I mean, wouldn't you want to not have an ad-based internet? Just go in a newspaper, pay 10 cents for the article, everything happens automatically. And I think lots of people would, but no one really tries to implement it, because you'd just crash the system. I mean, and if you do a sharding-based approach, which is what everyone else is doing right now to achieve the huge scalability, you'd be stuck with huge latencies, because if you have to do any cross-sharding payment, you essentially have to wait for 2 blocks, which any regular microtransaction usage would just be impossible. Another one, surprisingly, is voting systems. Several jurisdictions have tried to do voting on blockchain or on DLTs, but there is a surprisingly huge throughput that you'd need if you want to vote in the largest democracies in the world, which is India and the US. Like, if 200 million people vote in a single day, you'd get peaks of tens of thousands of transactions per second. And I've put online poker there, mostly because of the very first job I had. Right after college, I worked as a back-end developer for Full Tilt Poker. And in 2011, I learned that the US government can confiscate any internet domain, any .com internet domain, since they essentially forced Full Tilt to pay out all of their US user base. And I know everyone was afraid that Full Tilt had a rigged random number generator. I personally did one of the audits on that random number generator. It was perfectly okay. But what happened was that the owners of the poker site essentially just distributed all of the player funds as profits amongst themselves. And the regulator just didn't catch that. And I know I'm not actually condoning online gambling here, but there are certain, a lot of things that people want to do where you can't trust an auditor, even if they're doing a well-intent action. And the other obvious applicability is hugely scalable dApps, in that there is a need for payments. I mean, like Peter's talk yesterday, I'm not sure how many of you saw it, but if you want to do decentralized ride sharing, then you have to have a decentralized payment solution, a rating algorithm, and you would get huge volumes of transactions. And now I think I sped a little bit too much through all the slides, but I wanted to run a demo of a network. No. No. Yeah. So this is a testnet I created this morning of our current implementation. As you can see here, we use Linode, an AWS type service provider that is a little bit cheaper and a little bit more user-friendly. And it's a machine with 5 servers in the West US data center, 4 in their central one, East US, West US, Central EU, and West EU. And right now, all of these are 16-core machines, 64 gigs of RAM, and it's running at 130, trying to do 130 transactions per second. You can see here, these are all rounds. It's green when the entire network is in consensus, so finality has been reached. And red is rounds that are still being synchronized and produced by the entire network. It's essentially almost as a complete network. The only difference between this and a running mainnet would be that here we skipped, we used not the full signature verification scheme, because you would just need more expensive CPUs to handle this. We just wanted to see how much essentially the transaction processing engine could do. And let's try to turn it up. And this one has locker limitations removed. So it's essentially a test to see how much we can do. So let's first try to say 5,000 transactions per second. Oh. No, no, yeah, it did set. Yeah, so you can see now rounds take a little bit more time to get a finality on them. Yeah, but let's push it a little bit more. So each machine is essentially simulating a network of bots that are just trying randomly to to put in transactions in the system. And yeah, you can see here, you sometimes, round length is at 3 seconds here. And it might take a couple rounds to hit consensus. And now let's try to go even higher. You can see that actually the main bottleneck, the main bottleneck for this is CPU, because you have to process more transactions, but bandwidth itself. Each transaction is just around 470 bytes. But you do need an 11 megabyte connection to the internet. And let's see how far we can push it. I think this is kind of the furthest I've seen this run stably. Let's see. No, I don't think it changed. Yeah, so it takes a little bit more time now to get finality, just because essentially we had to optimize the entire system from the ground up in order to maximize performance. So from the network layering itself to the data structures internally used and to everything, it's all basically done in C++ by us. And I think it can handle a little bit more. We just use virtual machines here, so sometimes the performance is variable depending on what other people are running on those same machines. Yeah, and I guess at this point, if you have any questions, I'd love to answer them.
Hi. Is there something similar to a big O analysis of how it scales as you add servers, like linearly?
So no, right now the system can implement sharding on top of it. We know how to implement sharding on top of it, but the way it is done right now is the performance will get just slightly better if we increase the number of servers, but it will essentially just keep the same, because each server has to process the entire state in order to maintain the latency, because you never know when you'll be a locker to another account, so you have to maintain the entire state in order to get a confirmation. And right now, it's around a 200 millisecond confirmation from the locker, because it's just a ping with a random, let me just put it a little bit lower. No. Yeah. So we can do it much more scalably, but we wanted to make sure that first, before sharding, it is as scalable as possible per single machine instance. Yeah.
Here, thank you for the presentation. Do you incentivize lockers?
Yes.
If I'm living, for example, in Berlin, why would I want to put my stake my coins for somebody in, I don't know, Bolivia?
Well, we have a fee model, so transactions have a fee incurred on the network, and the fee is split between the lockers and the rest of the network. So lockers get a large part of the fee itself, just because they have to do a lot more work. They have to sign on the transactions.
Thank you for an interesting talk. I was just curious about, let's say you gave the use case of micropayments.
Yes.
And if you see a lot of payments to the same account, how does the system handle this?
Well, I've been asked this question before, and that actually is a lot of payments to a specific real person or real entity.
Like a retailer or like a
yeah.
Amazon.
And if you let's say you're Walmart and you've got hundreds of transactions per second, then you just have 1,000 accounts, and every time you have a payment, you just tell a person what account you want to receive that funds in. And this also gives you a different kind of benefit, because you could have latencies in the order of milliseconds, because you could assign an account that is in the same geographic area as both your customer's locker and your locker. So you can get that pre-approval, pre-signature in the order of milliseconds, because you're all in the same geographic area, and you're using the accounts in that geographic area.
All right, makes sense.
So first of all, thanks a lot for the amazing talk and the impressive performance.
Thank you.
So if you have to recommend to a app developer who wants to interact with your system to get kickstarted, so where would we find resources, and what is the best way to integrate your blockchain?
We're still working in progress, so we're hopeful by the middle of December to have a testnet ready. Right now, it's still closed source because we know we've got some issues to work out. Like there are a couple of attacks that we know we are susceptible to, and we want to just make sure that everything is working even for the testnet. But we want to open source the code a little bit before the launch. But we know at this point, I mean, it's still moving from being a prototype to actually being production quality.
Hey, do you have a website? Because I didn't find any.
Blink.network.
Thanks.
Welcome. All right. Thanks.